Okay. Mm, So camera basics. We will look at a number of components of the camera. Yeah, here. All right. So there are a few things that go into making an image, right? Of course, there is light. Without light, there is no image. We want to briefly understand the anatomy of the human eye. Okay, so that see, a lot of advances in computer vision have happened due to the understanding of how the human vision system works. Okay, so there have always been inputs from neuroscience, and so it is sort of useful to know how the human eye works. Okay, because there will always, when you read papers, there will always be some kind of references or comparisons with the human vision system. Okay. Then we'll look at some aspects of digital camera. And if time permits, I'll move on to the next uh, set of slides on lenses. Okay. Okay, so as we know, light is necessary for image formation and it strongly influences the image. Okay, and so when you take an image and you have, so for example, you have gone outside and in daylight you're taking an image, and then you sort of have no control on the lighting. Okay, so drone images, for example, uh, depend highly on the quality depends highly on the sort of day it was. If it's a cloudy day, you will have a different kind of image than what you'll get on a bright day. Okay, so so in that circumstance, it is not possible to control lighting. But if in industrial settings or if you're looking for robotics and this kind of thing, uh, if, if it is possible to control lighting, then it is advised to control it. Okay, because if you have a well lit or even not well lit, you have proper lighting, then it makes the pre-processing tasks much simpler. Okay, I'll show you examples. So lot of those pre-processing problems can be avoided if the lighting has been controlled or made as uh, as amenable to the task as possible. Okay, so there are various, when one talks about lighting, there are various kind of lights. So we will see one diagram which sort of uh, demonstrates all of these. Okay, so the object here is in the center and it's facing north. Okay, so front lighting is when the lighting falls right uh, or is directly on the object. Okay, so that is front lighting. Then on the left and right hand side of front lighting, you can see angular front lighting. Okay, then if the angle between this north and the lighting increases further, that's a dark field illumination. Okay. If you increase the angle further, it's angular backlighting. And if the light is exactly behind the object, that's called backlighting. Okay. So what happens? Various kind of effects that you get because of all these various lighting. So for example, if you have a direct incident light, what does it do? Well, a direct incident light definitely is going to be bright and focused. Okay. So beam angle, we mean the angle made with this uh, vertical y-axis. Okay. So it has a low beam angle and it results in a strong reflection. So this is something to remember. While it is bright and focused, you can also get something like this, which is something you may not want. Okay, and the other, so in this example here, you can see this reflection caused by the direct lighting. Okay, this is an artifact that you would prefer to not have if you're going to do segmentation in this example. Okay, because the pixels on this LCD screen here are going to be classified as white. Okay, suppose you are doing a binary segmentation, you want to change this grayscale image to a black and white. Okay, then, well, you would think that this screen should appear black, but this reflection here is going to cause these cells to appear as white. Okay, so that's an artifact that is going to be created because of this strong reflection. On the other hand, you can see that because it is so bright and focused, all the minor scratches on the screen are appearing so clearly. Okay, so this is an effect that you may not want. Okay, so you should know the pros and cons, okay, or at least have an idea of pros and cons of all these kind of lightings. Okay. Now the same object, if it appears in diffuse light. So what is diffuse light? Direct light means the light beam is appearing straight onto your object. Okay. A diffuse light, which can be obtained using a dome, or or putting some kind of semi-transparent object in front of the source of light. So that's called diffuse light. Okay, so the same object as before appears here in diffuse light, and here you can see that because of that light. So what happens when you diffuse the light is that the screen in front of the source of light will diffuse the light beams in various directions. Okay, so it won't be such a bright focused light falling onto your object. And so the spread out light is falling on the object, and that is why the image now looks like this. And this is possibly what you would like to have if you are looking to a segmentation job. Okay, so this kind of light is very desirable, bright but diffuse. Okay, not focused onto the object. Lateral illumination is one of those angular. Okay, when the beam angle is large, which means you have either angular front lighting or you have even further a slightly dark field illumination. So on the right hand side here, you see when the object when the light is focused straight. So this is front lighting on the left, and on the right, oh gosh, just a moment. Yeah, sorry. So yeah, here, so on the right here, this is, you can see that the light seems to be appearing from, the source of light seems to be somewhere on the left of this image, okay, or left of this object. And so here, the different components are being focused here, and different components are made clear in this. Okay, so lighting can really affect. So if you were interested in these notches, if you wanted to segment out these notches, then this kind of lighting would be more suitable for you. On the other hand, if you wanted to segment out this kind of these uh, components of the electronics, then front lighting would be more effective. Okay, so when you are able to control lighting, then you should think about what is it that you want to focus on. So here is this is an example of dark field. So now the beam angle is even larger. So this is dark field illumination. You can clearly see different things. So here, for example, if you wanted to read this, okay, if you want your program to be able to read this, then this is a more desirable sort of lighting if you want to read the letters here. Right? Here is another example of dark field illumination. Okay. So because the angle of incidence is equal to the angle of reflection, here what happens is that most of this is what I've written up there. The light is directed away from the viewer, and so the field of view, which means most of this remains dark, and only these inclined edges are lighted. This is an example of backlight illumination. So in this case, the lighting, the source of light is exactly behind the object. Okay, this kind of lighting is useful if you are interested in the silhouette or the edges of the object. Okay, and well, if one is really interested only in the edges, you can see how easy the task of segmentation is for this object. Okay. There are two kinds of backlight illumination. One is if the source of light is closer to the object, you will get something like this left hand side. Okay, because what happens is that the excess or the diffuse light from that closer source of light spreads to the other parts of the object. Okay, so on the other hand, if your source of light is farther away from the object, then the edges appear much clearer or sharper. Okay, so this is backlight illumination. Backlight illumination can also help recognize some things like this mechanical stress distribution on an object. Okay, so in this way, so backlight or on some transparent objects can help segment out these kind of artifacts which are already present on the object. Okay. Yeah, so any questions up to here? Anyway, I'm not going into too many details of this, but just trying to give you sort of an outline of the whole thing. Okay, so now let's quickly talk about the human eye. Okay. So this is a top-down image or sort of a cross-section of the eye. And from your biology class in school, you'll probably recognize all these components. Okay, so you have the cornea in the front. This is the pupil. This muscle band on both sides is the iris. The lens behind the pupil. Okay, then this is a sort of chamber, fluid-filled chamber, and back here is the retina. Okay, and this is the optic nerve that takes all the impulses to the brain. Okay, so this is a short description of the human eye. So the camera is based exactly on the working of the human eye. This is the two workings are very similar. Okay, so the human eye lens plays the same role as a camera lens will play. Okay, and the pupil plays the role of the aperture, and the iris plays, or I should say the other way, right? The aperture plays the role of the pupil. The shutter plays the role of the iris. So the job of the iris is to regulate the amount of light that falls onto this lens. Right? So if you're in a dark room, your eye would want to collect as much light as possible. So for that reason, the iris will, contract so that the pupil gets larger, and your eye can collect as much light as possible. On the other hand, if you are in a very brightly lit place, then the iris will expand so that the pupil gets smaller because you do not want to collect as much light. So that is the function of the iris. That is exactly the function of a shutter. Although the shutter does a bit more. Okay, so we'll get into that. Okay, and this the lens of the eye focuses the light. The objective is to focus the light on the retina. Okay. Now, what happens on the retina is that there are two kinds of cells there. There are rods and cones. And so I won't go into the depth, but I'll give you a good reference. And you can read more about this if you like. So rods and cones are, the job of rods and cones is to detect light and detect color. Okay. So they are spread in a certain pattern along the retina. Okay, and when light falls on the lens and it is focused onto these cells, they act exactly like photodiodes would. Okay, so the photon creates an impulse in the cell here on the rods and cones, and that impulse is carried by the optic nerve to the brain to process. Okay, so that is how the human eye works. All right. Now there are many aberrations, okay, or many eye problems that take place when this lens. So first, usually this is the human eye is sort of globular, okay, sort of round, okay, and the correct functioning of the eye depends on the correct shape of the lens, as you can imagine. and the correct shape of this globe. Okay. So for many reasons, if it so happens that the shape of this globe is either, elongated along the vertical direction, I mean this north-south direction, or elongated along the east-west direction like this, then the light cannot be focused properly. That is one problem. The other problem is could appear with the lens itself. Okay, so if there is a deformation or an aberration in the lens itself for some reason, then again the light cannot be focused properly. Okay, so these two things give rise to various conditions of the eyes. There are other conditions that happen because of other problems. So I'm not talking right now about that because I'm only talking about image formation as we would see in a camera. Okay. Okay. So yeah. So this picture just sort of explaining how the eye works exactly like, or the working or the image formation is exactly like that of a pinhole camera. Okay. So the light is entering through the pupil, focusing onto the falling onto the lens, and then so right in this image this is kind of simplified. Okay, we are not taking into consideration what the lens is doing to this light. This is sort of a simplistic image, and then the image is formed upside down on the retina, and of course your brain does the work of getting it into the proper orientation, and that is how you see. All right, so moving on. In a digital camera, as I said, the digital camera or any camera uh, works on this same principle as that of the human eye. So, like the eye, you have a lens, and like the pupil, there is an aperture. Like the iris, there is a shutter, and the work of the retina is done by retina rods and cones is done by this sensor. Okay. So we will talk about lens, shutter, and sensor, and the rest of this part I'm not going to talk about much because I'm not an expert in these things. This comes into optical engineering, and I don't know much about that. Also electronics. But the point is that, even if you think you're working with raw images, uh, you will not actually ever be working with totally raw images unless you get a special camera for that. Because what happens is that when the light falls on the sensor itself does a job of does various kinds of processing on the um, photon impulses that it generates. So there is some processing that is already done here. Okay, and then that is the image that you receive in your, I don't know, compressed as your JPEG or PNG or whatever file. Okay. So there is a considerable work that goes from the sensor to the processor also. And even your raw image is not entirely. Okay. So anyway, let's talk about the shutter, the sensor, and a few other aspects, and the lens of camera. Okay. So lenses, these are used to obtain images which are sharp, like we saw yesterday. They have to have good contrast, clear and undistorted. That is the objective of using lenses. Okay, so they will have good contrast if they can collect more light. That's what a lens does. Okay. The choice of lens always depends on the amount of available light, distance to the object, and the field of view. Okay, so these things, of course, cost also. Lenses are expensive, so it also depends on cost. So, but if you have a lot of money, then you will probably be worrying only about these three things. So these are broadly four kinds of lenses that are there. There are, of course, many other subdivisions among each of these. Okay. Uh, so a narrower field of view leads to lesser distortions in perspective. Okay, so we can see some examples. So this here is clearly a wide field of view. Okay, so you are trying to cover a huge area. So clear, this is an image taken with a wide angle lens. and you can see the distortion is absolutely clear here. You can see that straight lines are not straight. Okay, so uh, you have a lot of what is called as radial distortion in this image. Here is another example where the radial distortion is not so clear, but it is there. So first of all, if you see the image on the left, you can you can see the pillars. Okay, if you look at the pillars towards the outside of the image, they are more tilted than the pillars towards the inside. Okay, so this is an example of distortion. This kind of distortion that comes about from the lenses can be corrected using transformations. Okay, so let's look at a sensor. So each cell so sensor is like this chip, okay, on which the pixel cells are arranged. Each cell on that chip corresponds to one pixel. That is one picture element. Okay, and what it does, what every sensor cell does, is that it measures the amount of light that falls onto it when the lens is exposed. Okay, and it further, I mean, its job is not just to record it, but also to store that signal. Okay, and in more advanced or whatever you see now, in more advanced sensors that are coming up now, it does further job of processing some early signal processing in order to store that signal. Okay. There are two main, so these are again, this is again a very broad description. I'm not going into too many details. There are two main kinds of sensors, the CCD, that is the charge coupled device, and CMOS. This is complementary metal oxide semiconductor. Although CCD, I mean, all sensors are made of metal oxide semiconductors. But anyway, this is what the names are. So these are the main differences between CCD and CMOS. Okay, so the reason we are going into even this much is because I mean, in my experience, you are never removed, even though you could be purely working on, you think you're working on your neural network. You're never removed from the situation of image acquisition. Okay, sometimes you will realize that you have to go back to the image acquisition process and understand what were the components or what were the situations or environment in which the images were taken. Okay, and then you need to request your whoever the client is or whatever uh, to take the images in a different way. You need to tell them sometimes that if this is done this way, we can obtain better results on the uh, end of the pipeline. Okay, so these kind of things, it is always useful to know. Anyway, so coming to the differences, main differences between CCD and CMOS. So CCD, by the way, are the high quality, expensive ones, and CMOS are the slightly lower quality, cheap ones. Okay, the CCDs require very specialized manufacturing processes, and that is what makes them expensive. And the CMOS, on the other hand, does not require such specialized, can be manufactured using traditional processes, which I don't know what they are, but okay. And so they are cheaper. They also require much less power, which is why they are more popular in our everyday devices. Okay, so our mobile phones or laptops, these kind of whatever cameras you see on these devices, they all use CMOS sensors, not CCD sensors. Uh, the cons in CMOS sensors are that they tend to be higher in noise, okay, and they tend to create a low noise. Sorry, what they they. I mean, I have not written it here, but they tend to not distort, how do you say, the colors that you observe from a CMOS sensor are not exactly true to life. Okay, so that is one of the disadvantages of CMOS sensors. On the other hand, with CCD, you get really extremely good quality images. So here, I think, yeah, here's an example of CMOS versus CCD. Okay, so CMOS is the image on the left hand side. and on the right hand side you have an image with the CCD, and there are a few differences. So these yellow rectangles can make a few differences clear. Okay. And so for example, you can see on that stretch of road below, you can see more noise in the CMOS image than in the CCD image. Okay. And this thing about colors, the color of the tree or the color of that board there is more true to life in the CCD image than in the CMOS image. Okay. So there are these things come into play if depending on the application. Okay, entirely dependent on the application. So let's talk a little bit about sensor sizes. Uh, it is clear that large sensor cells can collect more light. Okay, but if you want a large sensor cell, then you require larger chips, which are more expensive to produce. And they also, if you have a larger chip on your camera, then you will require a larger lens, which is also expensive. So if you want large sensor sizes, everything becomes expensive. So here are some comparisons of sensor sizes. Okay, so the outer one here, of course, there is the biggest one here, I think. Okay, but there's this 36 wide, which is used on these kind of cameras. Okay, and the innermost one, the smallest one here, is what you see on mobile phones. Okay, on our smartphones. So this is the one that is most commonly used. Of course, as the sensor size increases, the quality of the image is going to increase. Okay, but one thing to remember is that it is not a direct proportion. Okay, so big sensor size does not directly imply very good quality, as we'll see, because there are other factors also that come in. Okay, so let's talk about those other factors. So there is something called a sampling pitch. Sampling pitch means the physical spacing between the, so these are two adjacent cells, okay, adjacent pixels in your image or adjacent cells on the sensor. You look at the center of these two and measure the distance between these. Okay, so that is called as the sampling pitch. By the way, you should know what this sampling pitch is, because commonly you might face a situation where you need to convert your pixel size to okay, or microns, or you need to do this unit change. Okay, so in unit change, the how many pixels fall in 1 micron, okay, or how many microns in 1 pixel, anything, either way. So for those kind of conversions, this pitch size is exactly what you require. Okay, so you will require the size of the sensor and you will require the pitch, the sampling pitch. Okay, so this is called sampling pitch. This is called as pixel gap, the gap between two cells. Okay, so in this image, although it is appearing, this is a simplistic image where it is appearing that all pixels are, sorry, all these cells are placed next to each other. But we will see later that it is not necessary that they are placed next to each other like this. Okay. Anyway, so the spacing, however, will be uniform, and that gap is called the pixel gap. And of course, this is called, the size of this cell is the pixel size. Okay, so three things to know. The number of rows and number of columns, because the sensor need not be square. The sensors can be rectangular in shape. So there might be unequal amounts of, unequal number of cells along the rows and along the columns. So, of course, smaller pitch will imply more number of cells, correct? So if you decide to have smaller pitch, which means you decide to close in this gap, okay, or you decide to increase the pixel size. Okay, so in either of these cases, the pitch will be smaller, which means there will be more number of cells. So the resolution will be higher. This is what it means by resolution. Okay, but what this means is that there is less area per pixel. So the number of photons So more number of photons are lost. So you can crowd in more pixels, more cells here. Okay, but if you crowd in more cells here, then you're reducing pixel sizes. Okay. Instead of having 5 here, if you had 10 here, that means you would, the sensor size is same. So that means you would be reducing the size of the cell to crowd in more. If you have crowded in more, that means there is more resolution. Okay, so that is why, that is usually how the resolution of a sensor is stated, right? These many pixels by these many pixels. So crowding in will mean more cells, but it also means that, see, every time there is a gap between the pixels, the light falling in those gaps is lost. The only light that is captured is the one that falls on the cell. Okay, so if you are making too many breaks here, that means you're losing more photons. Okay, you're losing more information. So smaller pitch will imply more number of cells, but this will also imply that more number of photons is lost, which makes the image noisier. Okay, so more higher resolution does not always imply better image quality. Okay. There is also something called the fill factor. So the fill factor of an image sensor is the ratio of a pixel's light sensitive area to its total area. So exactly, the total area is the total area of the sensor. Okay, and what is the light sensitive area, which means what is the area out of this that is covered by photosensitive diodes, okay, or these cells. So that is the fill factor. Okay. So finally, the quality of the image depends on this fill factor. If your fill factor is high, which means more light is being captured, you will get a better quality image. So it does not just depend on the resolution or the number of cells on that sensor. Yeah. So higher fill factor implies more sensitivity to light. On the manufacturing side, this is not the best thing, because if you arrange more pixel or larger pixels, larger cells, then there is less space for other components that have to also go on the sensor. Okay. So
Hello,
let's talk about that.
hello.
Yes.
Ma'am, what is this photons which you just spoke about?
Sorry,
So,
1 minute. I cannot hear you. Maybe I should increase the volume. Yeah, tell me.
yeah, ma'am, what is this number of photons are lost? Like, I did not get this.
So what it means is that here, see, only the light that is falling on the cell is going to be captured, right? The light that falls in this gap is going to be lost, right?
Mm-hmm.
So photons captured means the light that falls on this cell. The light arrives in the form, I mean, this is the theory that the light arrives in the form of photons. Those photons are captured by this cell, and that is the signal that is measured by the diode, right?
Okay.
So whatever light falls outside this cell is lost. So if you, yeah, so this is one thing to keep in mind in this image taking process. The light coming in can be thought of as a continuous signal. Okay. And that continuous signal, when it falls on the sensor and has to be recorded, that continuous signal is being discretized. Okay, the information that you're gathering is in a discrete form. So when the continuous signal is discretized, there is going to be loss of signal, which means there is loss of information. The information that fell on these parts is lost.
Ma'am,
Yes.
so each pixel, when it captures light, when it gets some kind of information from a particular type of photon, so that is responsible for only one signal, right? As in one shade of a color or whatsoever it is, right?
Yes.
Each
So
pixel.
yes.
So if the pixel sizes are big, then also information is lost because we are not able to capture the variations, right?
Yes. So that's a different kind of loss, color loss you're talking about.
Okay. Okay.
Right?
Fine.
So right now I'm just talking about simple information, loss of that signal.
Okay. Okay.
Okay, we'll talk about color towards the end of this.
Okay. Fine.
Yeah. So simply because you lose some part of the signal when you go from continuous to discrete. Okay, and that loss occurs exactly because you are not recording the photons that have fallen on other parts of this sensor. You're recording only those that fall on these cells. So now what the fill factor is saying is, on your sensor, how much area of the sensor is actually capturing these photons. Okay, so that's what the fill factor measures. What area of the sensor is actually capturing the light. Okay, so fill factor will be higher if you sort of either you have larger cells, okay, or you have more number of cells. In either case, your fill factor can be high.
Yes, ma'am. I get it. Thanks.
Yeah,
Yeah,
yeah.
yeah.
But now what is the difference between these two? If you have larger cells, you're losing less information because your larger cell is capturing more continuous information. If you have smaller cells, you will lose more information. Okay, even if your fill factor is high in both cases, there's a difference between how it is high. Okay. And the other thing is that manufacturers cannot keep the fill factor really high. So, for example, why cannot this entire thing be just 1 pixel cell? Okay, why then you would just have everything, right? But that is not possible because of all the processing that needs to be done with that signal later. Okay, so there is not just these cells, but other electronics that goes on this sensor. Okay, so manufacturers cannot keep the fill factor really high because they have to fit other things on this. Okay.
Also,
Yeah.
ma'am, one more thing. Addition of noise might lead to better visual features in the image, right? Because
Yeah, sorry. Say it again.
if if the noise is increasing due to lesser pixel size, that means
Mhm.
more number of pixels.
Mhm.
Still, images tend to be more sharp, and if we try to zoom it, it's more clear.
Yes.
Right.
So exactly. So I'm not saying any of this is good or bad.
Okay. Okay.
Okay,
Fine.
I'm just telling you the two sides. And see, in this whole business, there is nothing like good or bad.
Okay.
Okay,
Fine.
CCD or CMOS or whatever number of. The thing is, you need to be aware what is what, so that in your application you need to know what should be the correct thing to use. Okay, or you should have some idea of what should be used, or if this was used, then this is the artifact it is producing. Okay, so in this,
Yeah.
this is just facts. There is nothing like it's good to have this or bad to have that.
Also, ma'am, how is this that high resolution image would be more noisier?
So exactly this, right? Because high resolution, what does resolution? If you're by resolution, if we simply mean how many pixels are packed onto the sensor. Suppose you pack on more pixels here, okay? Then you will have those gaps in many more places.
Yeah.
The
But
discretization is higher.
ideally it should be like that. Higher resolution means better image, right?
So a bit better in the sense of what? That is also the question. Okay. So see, the artistic interpretation of an image differs, or artistic, what can be called as nice as artistically, okay, differs from what is useful industrially. Okay, so I'll show you some images where you might, if you're looking at it from a creative or artistic point of view, those are beautiful images. If you're looking at it from processing point of view, it's a nightmare. Okay, so so that is why I'm saying there's nothing like good or bad. It entirely depends on the application. Okay, so yes, you have more number of pixels, so you expect that the images, the quality is better. Okay, it's better to the eye. But you also have to keep in mind that if you're thinking of it as a signal, okay, then you have discretized the signal into smaller chunks. Okay, so there is a loss of the continuous signal in more number of places. Okay, and so they tend to be noisier. So this is one of the things to keep in mind.
Okay, okay, ma'am. So basically, you're emphasizing that it's different what we see and what computer like.
Yes, exactly. It is different what we see and what when the computer has to process it as an array of numbers. Okay, it's different from how you would perceive the image. Okay. Okay. So yeah. So this is about the shutter speed. So the shutter, like the iris of the eye, controls the amount of light that falls on the lens and hence the light that falls on the sensor. Okay. So if you have done some photography or have ever read something about it, then you know that the shutter speed is really important in photography, right? So if you want, if you've ever seen those images of the night sky, if they do this long exposure images where they leave the camera shutter open for a long time, and so as the earth moves, all these stars, these heavenly objects will have a tail, right? Have you seen those kind of images? Okay, so that is a very artistically nice or beautiful thing to look at. Okay, so that comes from more exposure. You expose the lens to the light for a longer time. Okay, industrially that's not a good idea because it leads to blurring. Blurring not bad, not good for segmentation. Okay, so if we are just thinking in this way, then the artistic things are not necessarily useful. So moving on. Yeah, so here actually the title here should have been the other way. It should have been global versus rolling shutter. Okay, so yeah, this is one thing that I had written there but did not mention, that the CCDs usually come with a global shutter and the CMOS comes with a rolling shutter. I'll tell you what each of these means. So actually there is a nice, let me just stop sharing this. I had a nice animation of this. Or we can just find it online. It was online only. So the global shutter, what it does, and the rolling shutter, what it does. Yeah, maybe I will just global versus rolling. Yeah, here. So let me share this. Because this image makes it clear exactly what is happening. Okay, so this is rolling shutter, and on the right hand side is the global shutter or total shutter. Okay, so what a rolling shutter does is it exposes a few pixels to light, or stops a few pixels being exposed to light at a time. Okay, so and the total shutter, well, all the cells are exposed at the same time. This is the difference between a rolling shutter and a total shutter or a global shutter. Okay, is this clear? What a rolling shutter is doing and what a global shutter is doing. Okay, so in a global shutter, you can see this is instantaneous. Okay, whereas in a rolling shutter, the first row is not being exposed at the first instant of time. The second is not, the third is not, and so on. Okay. So that is the difference between a global shutter and a rolling shutter. Okay. And the artifact that it produces in the image is like this. Okay. So on the top is the global shutter, and on the bottom is the image obtained with a rolling shutter. Okay. So what is the difference? You can clearly see the difference, right? So since all the cells were exposed to light at the same time, the top image has been actually captured at the same instance of time. Okay, so that difference is seen in the blades of this helicopter, right? On the bottom, it's a rolling shutter effect, which means that at the cells were exposed to light at different instances of time. Okay, and in between those instances of time, this blade has moved. Okay, these blades and these blades have moved. So if the speed of the object whose image you're taking is more than the speed of that shutter, then you will observe this kind of curve, okay, or this kind of artifact appearing in the image. Is this difference clear?
Ma'am, is it a need for CMOS cameras, CMOS cells to go for a rolling shutter? Because
This I don't know. This is actually, I mean, somebody for an electrical or electronics engineer.
okay,
This
fine.
question. Okay, this I don't know why they are always coming like this. Why CMOS is always paired with a rolling shutter and why CCD is always paired with a global shutter. This I don't know why.
Okay.
So, but these are the effects that. So, I mean, the lower image, there is nothing good or bad, right? I mean, if you're an artist or if you want to do something creative, you would prefer having this image on the bottom. However, if you are interested in measuring the length of the blade, you would prefer to have the image on the top. Correct? So it depends on the application. All right. So this is the difference between a rolling. This is one of the things, one of the artifacts. The other artifact is this. Okay. So on the left hand side is an image with a rolling shutter. On the right hand side is an image with a global shutter. And the reason for the difference here is that so this image is taken with a flash, and the moment the flash appeared for the rolling shutter was when these pixels were not being exposed to that flashlight. Okay. On the other hand, here the global shutter opened exactly at the moment when the flash appeared, and so all the pixels could gather light at the same time. Okay, so this is another effect that can appear because of a rolling shutter. Okay. Okay, so now we come to color. So the pixel cells that we were talking about all this time, okay, that was the idealistic picture or the how do you say, simplified way of looking at it. But now when you want to take color into consideration, there are actually two kind of cameras. There is a 3-chip camera and there are single chip cameras. Okay, so a 3-chip camera of course is very expensive, but what is good with a 3-chip camera is that there is a sort of a prism kind of arrangement here, and what it does is it splits the light into 3 beams, which are now collected on 3 chips, each of which is sensitive to a particular wavelength. Okay, so these here are collecting all the red. These are red pixels, which means they collect the information coming from the red wavelength. Okay, these collect green and these collect blue. Okay, and now these are aligned pixel to pixel. Okay, and when the information on all of these is collected, the information will appear as 3 arrays of red, green, blue. Okay, 3 different arrays, and that is your RGB image. Okay, so this is how a 3-chip camera functions. So it actually, so what is the advantage of this? The advantage of this is that minimum information is lost because you are all these cells are collecting all the possible information coming from the red wavelength. These are collecting all possible information. I mean, you know, modulo that loss that is happening because of continuous to discrete, modulo that, we are collecting as much as possible from the green and as much as possible from the blue. From all three wavelengths, we are collecting as much as it is possible. Okay. So that is why this 3-chip camera will give you sort of the best quality or the best information preserved. Okay. On the single chip camera, on the other hand, you will these red, green, blue cells. Okay, I'm just calling them red, green, blue cells, but what they are doing is collecting red, green, blue light. Okay, so these cells are arranged in certain patterns. Okay, so here you see there is nothing, no filters applied. So this is just monochrome. Okay, and the result of this will be a grayscale image. But you can see all these different patterns. Okay, so this CYGM and CMYW, these are other color spaces. So we will talk about color spaces a little later. Then we will talk about this. Okay. So this is cyan, yellow, green, magenta. This is cyan, magenta, yellow, white. Okay. So these colors. So these are also like RGB. These are also color spaces. The Bayer pattern is the most I think oldest, I don't know, but very common pattern. Okay, but other companies can have their own patented patterns, different patterns that their engineers will explore. Okay. All right, so let's just take a closer look at the Bayer pattern, and then I think that will explain what this does. Okay. By the way, what is the time? Okay. So this is how color interpretation happens in this one. Okay. So you have only these four green pixels here. Okay. These are four red pixels, and there is one blue pixel in between. Okay. But when you see the result of this image, okay, as an array, you will have three arrays: one of red, one of green, one of blue. Okay, well, here if there is only green, then from where are the red and blue values appearing in the matrix? They appear by interpolation. Okay, so this is the processing that I was talking about. This is one piece of processing that needs to be done on the sensor, this interpolation. Okay, so for example, if this is a blue pixel, then for this pixel, the corresponding values on the red and green matrix should be 0. But that is not what happens. Okay, what happens is for this cell here, this element, the interpolation will be done from these four red cells. Okay, the values of these four, whatever the intensity is captured in these four cells, those values will be interpolated. And this is just one example of interpolation, by the way. There could be other formulae that can be used by different manufacturers. So the point is that some interpolation is used to calculate the red value for this cell and the green value for this cell. And so in the end, this cell will have all three red, green, and blue values. And so the number will not be 0 in the corresponding three matrices. Okay. So this is how color information is stored or captured. Okay. So in a single chip sensor. So if you have, you can imagine that instead of this single chip, if you had 3 different chips, you would be, for every cell, you would be, or every spot, you will be capturing the actual values, actual red, green, blue values, right? But of course, with 3 chip cameras, the cost goes really high. And what this does is not bad at all, as we see in our cameras, right? So that's not a bad job for everyday uses. And so this is cheaper to produce. Okay, any questions about this? Or till here? Okay, so since we have time, I will also open up my other set of slides about lenses, and then we can just finish off the topic today. So lenses and aberrations. Well, you must be remembering from your physics maybe that there are different theories of light propagation, right? There is the basic geometric or ray optics. There are many intermediate theories also, as physicists came up with more and more advanced ways of explaining how light propagates. But the three main, like for rudimentary understanding, this geometric or ray optics is sufficient. Then there is wave optics. In order to understand the various wavelengths of light, you require the wave model. And then there is quantum optics based on this wave particle duality. Uh, for our purposes, it is enough to talk about ray optics to understand again the basics of how image is formed, and a little bit of wave optics later, just to understand color. Okay, I mean, we are not doing physics, so it won't be too deep. So this, as I said yesterday, these are some basic laws of geometric optics or ray optics that you have seen in school. Okay. So I think we revised this yesterday also, correct? One of the important things is that intersecting rays do not influence each other. Okay, otherwise, they would have been chaos. Then we saw yesterday, we revised the Snell's laws also yesterday. And then this is one of the, so there is what is called as first order, second order, third order optics. Okay, there is, if anybody has studied optics in your undergrad, then you will know that there are this. So what does first order, second order, third order refer to? This order refers to Taylor expansion. Okay, so you have a Taylor series. If you are considering just first order approximation to your optical element, that's for first order optics. Okay, second order optics, third order optics, and so on. Okay, so yeah. So this is in the paraxial or first order optics when you're just going to use a linear model. Okay, then you make the assumption that the angles alpha 1 and alpha 2 are small, so that you can ignore this sign. Okay, and just sine alpha will be approximately alpha in that case. So what this means is that if you make the assumption that these angles are small and use that n1 alpha 1 is approximately n2 alpha 2. Okay, so this assumption is made, then that is your first order optics. Okay. Now, so in geometric optics, this is what we will assume. Yeah, we don't need to go too much into the depth with that. So there are two basic models when one talks about lenses. There is the thin lens model and the thick lens model. Okay, so in the thin lens model, this is very close to the ideal thing. That means what you would get without a lens. Okay, so but the thin lens model is very inadequate in explaining what happens in real life, because you cannot really create such a thin lens that will act as if there is no lens. So usually one looks at a more realistic model, which is the thick lens model, in which case the only undeflected ray is along the optical axis. Okay, so this is just one thing that we need to remember, that the only undeflected ray when we are talking about lenses is along the optical axis. Okay, so the optical axis is where there is no deflection. Okay, that is the point to remember. Then if there is reason to look at it later, then I will give all these names, but right now we don't require these names. Okay, so I'm going to skip it. Now, the point is that we need to understand aberrations. Okay, so what is aberration? The aberration is defined as a departure of the path of electron beams from the path of the ideal imaging. Ideal means this paraxial imaging. This is what you would have ideally. Okay, but in real life, that is not what happens. Okay, so whatever is that departure from the ideal, that is called as an aberration. And there are various kind of aberrations. Okay, and in the first order optics, these aberrations are not clear. If you just use the uh, first order approximation, then that does not differentiate between these aberrations. But third order approximations differentiate. Okay, so these are called as Seidel aberrations, and there are 5 types, and these 5 types of aberrations can seriously affect the image quality. Okay, and some of these can be corrected, and some of these have to be corrected. I mean, some of these can be corrected with processing, and some of these have to be corrected at the image taking level. Okay, so there are 5 of these. We'll look at each of these in quick succession. The spherical aberration. So spherical aberration happens if the rays that enter this outer edge of the lens. Okay, so the ray enters a lens, and then it is um, then it converges, right? So this is convex on this side, so the ray converges. So after converging, the lens will bring all these rays to focus at a point. Okay. Now, if the point of focus has to be on the retina, so now this is like or on the sensor. Okay, but if that point of focus is either on this side or on this side or later, okay, so that focal point is not on the retina. Okay, but if it is earlier or later, then you don't get perfect focus. Okay, and so spherical aberration happens if the focus is nearer to the lens, is nearer the lens than the rays which enter near the center of the lens. No, there is something wrong in this statement here. Sorry, I'm just trying to. Okay. So what? Okay, so my understanding was slightly different. So what this is saying is that, well, the rays that are coming in from near the center of the lens are brought to focus at one point, and rays that are coming in from the edge of the lens, okay, from this top edge or bottom edge, they are brought to focus earlier than where the central rays are coming. Okay, so this causes, so there is going to be not all rays are focused at the same point, so there's going to be a blur. Okay, and so on the top here, there is these orange rays are showing no spherical aberration, which means whether the rays are at the center of the lens or at the edge, they are all being focused at the same point. Okay, so that is what perfect focus means. On the bottom side, they have shown what is spherical aberration. So the blue ray and the orange ray here are towards the center of the lens. Okay, and they are getting focused somewhere here. Okay, on the other hand, the dark orange and the red one, which are closer to the edge of the lens, are getting focused earlier here. Okay, so this effect is called as spherical aberration. Okay, so this is the effect of a spherical aberration. Okay, so this is perfect focus on the left hand side, but if you don't have perfect focus, then you will get a blurred image like this. Okay, and because what is happening is that the focus is happening here, and then the rays that go ahead here are going to create this region of blur. Okay, So that region of blur appears in the image like this. Okay, so this is spherical aberration. So there are a few details to be looked at in spherical aberration. There can be longitudinal spherical aberration, and there is longitudinal and transverse, which means you can measure the blur vertically or horizontally. Okay, so that's longitudinal or transverse, and this is so between this point and this point is what is called as the circle of least confusion. Okay, so well, if time arises, if there's a reason to talk more about this, I will talk more about this. But for now, I think we can let it go. Okay. So anyway, the point is that the spherical aberration causes a blur in the image. Okay. So this is 1142. Then there is chromatic aberration. Okay, so which is like a spherical aberration, except what happens is that the oblique rays do not focus. Okay, so axial rays will focus, but rays that hit the lens in an oblique manner, they do not focus. Okay, so the image appears something like this, like a cone. Okay, this is called coma or chromatic aberration. Okay, and there is the chromatic aberration can be corrected using using a device. Okay, so this can be something called RCC. Okay, so without an RCC, the image would have appeared like this, but with RCC, it you can see that this aberration is sort of reduced. So chromatic aberration can be is one of those aberrations that can be rectified on the camera level. It cannot be done with pre-processing. Astigmatism is when the lines in the object perpendicular to each other, say here, okay, they do not focus at the same point. Okay, so this kind of effect is very common in the human eye. Okay, so astigmatism is a very common aberration of the human eye also. Okay, so this is what is happening. These light rays are focusing. They should be focusing here. Okay, but they focus somewhere before. Okay, they could also be focusing after. Okay, that can also happen. So that is astigmatism, and this is the kind of image that you see because of astigmatism. Okay. Yeah. So then there is curvature of field. So curvature of field happens when your paraxial rays, that means rays which are parallel to the optical axis, are focusing at one point, and like coma, the oblique rays are focusing at another point. Okay, and now what is happening that the different oblique rays, all these focusing points form a sort of curve. Okay, so you have, instead of having your field of focus to be this sensor, your field of focus is now actually some kind of curve. Okay, that is called curvature of field. And a curvature of field is used nicely in artistic or to create very interesting artifacts in images. So here is an example. Okay, so in this image you can see that this pole is appearing very far. Okay, whereas in this image it appears so close. Now if you look only at this image, you might make some guess about this distance, whereas if you look at this image, you can see that the distance is actually quite far. Okay, so this kind of tricks can be, so actually the left hand side image is the actual, displays the actual thing. Okay, so the actual distance is displayed here, and the right hand side image is the trick appearing because of this curvature of field. Okay, so they can make parts of the image appear closer than where they actually are. Okay, so this is an example of curvature of field. And finally, so there's a note here that the earlier types of aberration degrade the image quality, and they have to be fixed during the image taking process with better lenses or by varying the focal length, distance, aperture, etc. Okay, coma aberrations in particular will damage the image permanently, and they cannot be corrected using post-processing software. And the final aberration that we are looking at, called distortion, this degrades only the geometric quality of the image, and distortions can actually be corrected using post-processing transformations. There are two kinds of, so maybe I will stop. Okay, this is it's already 11:45. Maybe you have a class after this. So, and this part needs a little bit discussion. So I will talk about this on Tuesday. Okay. Any questions so far? Okay. So if there are no